In section 4.2, we're going to look at binomial probability distributions. Let's consider the following experiment. Suppose we're going to pull a single card from a deck of 52 cards, and this game will be of the form that if you pick out a diamond, you win. If you pick out any other type of card that's a non-diamond, you would lose. We're going to repeat this process 5 times, and the selection is going to be done with replacement. So we pick a card out, you look at it, if it's a diamond, you win. If it's not, you lose. We put the card back in the deck, and then we're going to repeat this procedure. We're going to do this 5 times. So one of the things we're going to have is we're going to have a fixed number of trials. We're going to call that n. In this case, it's 5 times. It's important that for a binomial process, the trials need to be independent of each other, hence which is why the selection must be done with replacement. We saw earlier in this unit on probability that if we have selection with replacement, then that will produce independent events. And then the second key thing for us is we need to sort and kind of organize the outcomes into 2 distinct outcomes. In this case, one of which we're going to label a success, and the other of which we would label a failure. And don't think in terms of like positive or negative connotations, because depending upon the setup, success may be undesirable, whereas failure might be desirable. But just know that for a binomial process, kind of like the word binomial implies, there's 2 things that could happen. One of which we'll label a success. In this case, that's getting a diamond. And in the other case, it's going to be a failure, which would be getting a non-diamond card. And then the other thing is that we need for the probability of success to be the same on each trial. Because the selection is done without replacement, we know that the probability of selecting a diamond would be 13 out of 52, and that would be true for all of our 5 different selections. So n is 5, the number of trials is 5. The probability of success is going to be 13 diamonds out of 52, which would be a probability of 0.25. We will label the probability of failure is going to be labeled Q. Q can always be found by doing 1 minus P, because after all, the complement of being successful would be being unsuccessful, which means to fail. So Q will always be 1 minus P. In this case, that's 1 minus 0.25, which is 0.75. And now this is very important. The random variable for this experiment is the number of successes. So we want to keep track of what is the number of successes possible, and that will always range from 0 up to n. So it's possible that maybe we play this game and we're very unlucky, and all 5 times we get something other than a diamond, so we wouldn't win any, we would have 0 successes. It's also possible that we win maybe exactly once or exactly twice, or maybe we're extremely lucky, and every single time we pull out a diamond card, we could be successful 5 times out of 5. But always important to consider the range for your x variable. It will always range from a minimum of 0 successes up through all the way up to the maximum number of successes, which in this case is n. So we have 0 through 5. Let's take a look at a couple situations to kind of get some practice identifying these key concepts. In a survey, let's suppose that 57% of adults like texting because it is quicker than calling. We're going to ask this question to 9 adults. They're going to be randomly selected. Let's find the following information for this experiment. So first of all, this would be a binomial process because there's going to be 2 outcomes. People either do prefer texting or they do not prefer texting. So you could label that they do prefer texting a success. If they don't prefer texting, then that would be our failure. We're doing this experiment 9 times because we're asking 9 individual people, so n is 9. The probability of getting a success, in other words, getting somebody that does prefer texting, that's 57% of the population, so that would be 0.57. The probability of failure would be 1 minus p, which is 0.43. And then for our random variable x, if we ask 9 people, we could get anywhere from 0 responses saying that they prefer texting, all the way up to 9. So 0 through 9, those would be our values for the random variable x. Let's take a look at example 2. Let's suppose that we have a multiple choice test that consists of 4 questions in which each question has answer choices A through E. If we have no idea what the correct answer is and we try to guess, then this would become a random experiment in a random process. Again, there's 2 outcomes. Either we answer the question successfully or we answer the question unsuccessfully. Because we have to answer 4 questions, each question we can think of as our trial, and we're going to repeat this 4 times to answer the entire test, all 4 questions. So n is 4. The probability of success, so what's the probability that we answer a question correctly? Well, we assume that there's going to be just one right answer, and if we have choices A through E, that's 5 choices altogether, one of which will be the right answer, so that's going to be a probability of 1 out of 5, or 0.2. The probability then that we fail, or that we answer a question unsuccessfully, would be 1 minus p. That's 1 minus 0.2, which is 0.8. And for our random variable x, it's going to range from 0 up to 4. The next step is we might want to ask the question, well, let's suppose we take this test. What's the probability that we get exactly 3 out of the 4 questions correct? And for this, we're going to be using, in our calculator, the binomial PDF formula. This is a binomial of n, p, and x. Let me show you what the formula for this would be. So if you wanted to do these kind of calculations by hand, the probability of exactly x successes is found by taking n factorial, which was the number of trials, dividing it by n minus x factorial times x factorial, all in the denominator. Some of us might recognize this portion of this formula. This is actually n choose x. So from a collection of n items, how many can we choose x of them where order doesn't matter? Times p to the x, so this is the probability of success, of which we're going to have x of them, times the probability of failure, of which if we have x successes out of n, then we would have n minus x failures. So if you wanted to do this process out by hand, this would be the formula for it. Okay. For us, we have a formula in the calculator called Binomial PDF. This is under a brand new menu for us. It's going to be under the distribution menu. To get to the distribution menu, it's going to be the second vars key. So I need to hit the second function, vars, and now I need to scroll down a little ways until we find binomial PDF. Okay. Under the distribution menu, it should be option A. Now be very careful because there's one below it that kind of looks similar. There's a binomial PDF and there's a binomial CDF. For us, we will only ever use binomial PDF in our class. Okay. And now I'm going to go ahead and hit enter. And for those of you using the TI-84, you're going to see this kind of entry input. It's going to ask for the number of trials. We're doing our question example, so there's 4 questions. The probability of success on a single question was 0.2. And for x, we're looking for the number of successes, which in this case is we want the probability of getting 3 questions correct. Okay. I'm going to go ahead and hit enter, and this will paste it on the home screen. For those of you using the TI-83, you will not get that previous screen that you just saw. When you go to second distribution and you go scroll down and hit binomial PDF, what that will do for you is that will put the binomial PDF command on the home screen. It's up to you to kind of memorize the order in which the 3 inputs have to go. So there's something a little bit you have to bring to the table here. But the inputs are in this order. It's N, P, and X. The number of trials. And then you're going to hit the comma key, which is above 7. Then P, which is the probability of success on a single trial. And then comma, the number of successes you're looking for. If I go ahead and hit enter, we would see that we would get a probability of 0.0256. So the probability of getting exactly 3 questions right on this exam is going to be 0.02, let's say 6 to 3 places. Okay, not very good odds. Furthermore, it would actually be it would be unlikely. It would be an unusual event. Now that we know how to compute an individual binomial probability, we can do some other ones. For example, if you wanted the probability of at least 3. So we know that at least 3 means 3 or more. Now in this setup, so it's good to always kind of have your random variable x listed out so you know what that means. For this experiment, 3 or more would include the outcome of 3 and the outcome of 4. So I would take p of 3, which we just computed. I also need p of 4. Let me go ahead and get that. So again, this is second distribution. I'm going to scroll on down until I find Binomial PDF. There it is, Binomial PDF. And my trials is still n. Probability of success for a single question is still 0.2. But now I want to compute the probability of 4 questions correct. Going to go ahead and hit enter. For those of you using the 83, you'll do Binomial PDF. You have to put 4, comma, p, comma, 4. Again, that's npx. Go ahead and hit enter. And that would give us a probability of, to 3 places, 0.002. So we can go ahead and add them together, and we get that the probability of answering 3 questions correctly on this exam is 0.028. Let's take a look at the next one, the probability of less than 2. So if I go back less than 2, for this experiment would be either 0 or 1. So we would need the probability of 0 plus the probability of 1. Let's do the probability of 0 first. It's second distribution. Scroll down until we find Binomial PDF. And now I'm looking for the probability of 0 successes. Change x to 0. Go ahead and hit enter. And we would get that the probability of answering 0 questions correct would be 0.410 rounded to 3 decimal places. One of the tips I can kind of give you for this is, especially within an individual question, you're probably going to have to do several of these binomial PDF calculations. A faster approach than having to go through the menu every single time, second, distribution, and scrolling down, is that once you've already done one of them, one of the calculations within that particular question, you can use the second entry key to rattle off some more of them pretty quickly. So instead of doing the menu, if I want to now, let's say, find the probability of exactly 1, I can do second function and then hit the enter key. And what that does is that pulls up your previous entry in an editable style format. So I can now kind of go through this, and I can change the numbers if I want to. In particular, to find the probability of 1, all I'm doing is changing the number of successes from 0 to 1. I can then go ahead and hit enter, and that's a way to kind of do these really quickly. If I want a probability of 3 again, I can just do second enter, change the 1 to a 3, and in my opinion, it's a much faster way to kind of go through a lot of these than having to continue to go under that distribution menu, scroll all the way down, and do the command every single time. Okay. Either way, we found the probability of exactly 1 successes was 0.410 as well. So the probability of less than 2 is 0.41 plus 0.41, which will give us 0.82. To find the probability of at least 1, in this setup, the direct approach would say, okay, at least 1 means 1 or more. So that'd be 1, 2, 3, and 4. You'd have to take all 4 of those probabilities and add them together. Or we know that the way that we should be approaching this, we have the at least 1 rule. Using the complement at least 1 is the same thing as 1 minus the probability of none. We know that the probability of 0 successes was 0.410. So the probability of at least 1 will be 1 minus 0.410, which is 0.590. Let's take a look at another one. I don't have the statement of the problem. I think it was a certain surgery, so we have a surgical procedure that is successful on 70% of the patients, and we're going to have a surgeon that does exactly 7 of these surgeries. So if it has a 70% success rate, then P is going to be 0.70. It's performed on 7 individuals, so the individual surgeries repeated 7 times, so that's going to be N equals to 7. The probability that it's unsuccessful, which would be our probability of failure, is 1 minus P. That's 1 minus 0.7, which is 0.30. And as always, the random variable will always range from 0 up to N. So in this case, it's going to range from 0, 1, 2, all the way up to 7. The first part of this question says, find the probability that exactly 5 patients have a successful surgery. So we want P of exactly 5. So I'm going to go to my second distribution. We're going to scroll all the way down until we get to Binomial PDF. Hit enter. We have 7 is our trial size. The probability of success on a single trial was 0.7. And if we want to have exactly 5 successes, then x is going to be 5. Go ahead, we paste this and hit enter, and we would get that the probability of exactly 5 successes would be 0.318. So 0.318, it rounds. We could ask the question, what's the probability of at least 5 patients having successful surgeries? At least 5 would include 5, 6, and 7. So we would need to take P of 5 plus P of 6 plus P of 7. Well, from the previous part, we already have P of 5, so we know that value, but we also need P of 6 and P of 7. Again, the fast way to get those is to do second entry. Simply change the 5 to a 6 first, and that would tell us that the probability of 6 successes would be 0.247. And now we need the probability of 7 successes. Second entry, change the 6 to a 7, and we see that the probability of exactly 7 successes would be 0.082. Add them all up, and we find that the probability of at least 5 successful surgeries on patients would be 0.647. In part C, they want the probability that we have less than 5 successful surgeries. So less than 5 in the setup, if it's less than 5, that would include the outcomes 0, 1, 2, 3, up to 4. So you could go through, do P of 0 plus P of 1 plus P of 2, all the way up to P of 4. Or one of the things you might be able to observe is that the complement of at least 5. So if we do not have at least 5, then that must mean that we have fewer than 5. So the question that we're asking for in part C is actually the complement of the one that we did in part B. So the easier, faster approach would be simply to use the rule of the complement. It would be 1 minus 0.647, which gives us 0.353. So now we know how to calculate probabilities, binomial probabilities, using the calculator. The next thing we're going to look at is the mean, variance, and standard deviation of a binomial probability distribution. At the end of the day, these still are probability distributions, so they still behave like the objects we saw back in 4.1, and we already saw previously how to calculate these values. The way that we would do this, if you had the probability distribution, to recall, if you go to your stat menu, you would go to Edit, you would put all of the x values in L1, you would put the corresponding P of x values in L2, and then you would do a one variable stat L1, L2, and that would give us the mean and standard deviation, and then you could simply square that to get the variance. Okay. However, whenever we have a binomial probability distribution, these actually give us some shortcuts that will save us from having to do all of that, which is kind of nice because just alone, for example 3, the data entry would be pretty intense. You'd have like 0 through 7 in L1. You would need to compute all of those probabilities, P of 0, P of 1, all the way down to P of 7, before you could even calculate these. But if you have specifically a binomial probability distribution, there's these shortcut formulas defining those values. The mean of a binomial probability distribution is just n times p. The variance, sigma squared, is n times p times q. And the standard deviation is the square root of n times p times q. If we go back to example 1, where we had n was 9, p was 0.57, and q was 0.43, the mean can be found by doing n times p, that's 9 times 0.57, which gives us 5.130. The variance, which is sigma squared, is n times p times q, that's 9 times 0.57 times 0.43, which is 2.206. And to find the standard deviation, all you're doing is taking the square root of that variance. To do the square root, I would do second square, and it was 2.206. Hit enter, and we get about 1.485. So much simpler if we use the shortcuts for the binomial stuff. Let's look at one example. Let's suppose we have a binomial probability distribution such that n was equal to 84, p was equal to 0.65, and q is equal to 0.35. This is certainly one where you do not want to use the approach from 4.1. Here, our random variable would range from 0 through 84, so there would be 85, technically, 0 through 84, different binomial probability distribution calculations you would have to do just to get your L2 list filled out. However, we don't have to do that. We have shortcut formulas. The mean is n times p. That's 84 times 0.65, which would give us 54.6. The variance is n times p times q. So I'm going to take 84 times 0.65 times 0.35, and that's going to give me about 19.11. And then to find the standard deviation, it's just the square root of n times p times q. So we're doing the square root of 19.11, and that's going to give us about 4.371.